Okay. Oh. Okay. All right, so welcome back. The second exam is over, so that's good. And the average was a little bit below 60%. I've seen worse. Not much worse, but you guys did all right. And the curve was got everyone back on the same page. So I guess I would say it would be nice if you felt like you struggled with some of the problems, especially concerning differentiation, just some of the more basic stuff, to go back and take a look. I haven't actually posted the answers or the exam, but I'll put that up this week, and you can go and review and ask some questions if you have them in your recitations. Today, we're going to keep moving. And if you really, really loved what we were doing before, I'm sorry to say that we're going to take a break from differentiation and go into integration, which is generally much more difficult than differentiation. Nonetheless, there are some tools here, and we want to investigate them, what we can do in many variables. So just to reorient and recall, so we're going to talk about chapter 5 today. Start chapter 5, section 1. But let's recall what happens in one variable. And in particular, a lot of people finish first year of calculus without, I think, ever really necessarily understanding the amazing results of calculus. And that there are two sorts of, and here's what I mean by that. There's two sorts of things going on with an integral. Okay, one is there's this notion of an antiderivative, and then there's the notion of the definite integral. And the amazing thing about calculus is really the fact that these two things talk about the same, these two things are really giving you an answer to the same question. Let me put it that way. But the thing I think a lot of people miss is that they're actually really different. Their definitions and their meanings are very different. And so that's what I want to recall here, because we're going to have to do this in several variables. So what do you do to get this definite integral? So this is the way a definite integral looks in one variable calc. What is this thing? It is not, when you define it, it has nothing to do with derivatives or antiderivatives, nothing at all. What it has to do with is you take an interval, say from A to B, your endpoints, and you have your function f. Okay. And what you do is you take a partition of AB. So you partition AB, the interval. And what that means is you just sort of slice it up. You slice up this interval into bits. So let's call A x naught. And we'll take x1, go up to x sub n. And sometimes you evenly space this, but it's not necessary. You can also sort of, just as long as you're increasing, it's okay. You take these del xi's to denote the length of the subintervals. So this is a partition, right? So what it means is it means that we're taking this guy and we're just breaking it up. A is equal to x naught, We break it up, x2, until we go all the way to x sub n. And then when we want to look at this thing, we're just looking at one of these subintervals and finding their length. Right? That's the length, that delta of xi. And what's the goal? Well, the goal is we want, actually, at the end of the day, we want this to represent the area here. We want that to represent the area, but that's a hard kind of notion for an arbitrary function. So what we do is we take this breakup and we draw these, well, we can imagine drawing this sort of lines here. I'm not going to do it yet. Imagine just thinking about this function over these sort of subintervals. And then we want to, and what we want to do is we want to add the areas for each of these subintervals. But in order to do that, we have one more ingredient. What is it? So we choose the partition and choose this, and we'll choose one other thing, one other set of things. What do people know what it is? Everyone's taken one variable calc. What else do you need to choose to form something that's going to approximate the area under that curve? I'm sorry? Height? Okay, good. That's a good statement. You need some height, right? You need some height. And in order to get a height, what you need is what's called a sample point. You choose a sample point in each of these subintervals. So you choose sample points. And there's a typical way of doing it. You get midpoint or a right endpoint or a left endpoint. But generally speaking, you just allow yourself to choose whatever you want. And you write them as x sub I star. And that gives you your height. So we choose this x sub I star. Let's say this is, so where is x sub I star? X sub I star is going to be between these two. So it's going to be somewhere in between, somewhere in the interval that you're interested in. So this would be x sub 1 star. You take that x sub 1 star, let me just, and this is what you'll use to find this height. So straight up, we'll put that in. And then what that height that we get there is going to be f of x star. Right? And then we make a rectangle. Right? And we do that for each of these subintervals, and we add everything up. And what we get at the end of the day, this is all review, is we get something called a Riemann sum. I equaling 1 to n. Our height is going to be f of our sample point, our ith sample point, and the length of the base is this del xi. And that each one of these gives us one area of one of the rectangles, and we add them all up. This is what we call a Riemann sum. Now, what is the definite integral? The definite integral is a very, very fancy type of limit. So then the definite integral is defined to be this massive limit as what's known as, so if we think of this choice of points, of all of these choices we have, the sample points in the partition as being P, we can talk about the norm of our partition going to 0. That's sort of the maximal length of any of the subintervals. We want that to go to 0. So we want to take finer and finer partitions. And for each of these, we form this Riemann sum, and we're looking for the limit there. This is the definition of the definite integral. And as I was saying, it deeply saddens me that, that this definition is not sort of the way that a lot of people think of this definite integral. Because the beauty of calculus is relating this to antiderivatives and to being able to compute this. So this is what it is. And what we want to do now, as I said, is we want to think of what the two variable generalization of this notion is. And then we'll give ourselves some computational techniques to be able to evaluate it in some cases. Okay. That's the end of our memory lane. Once we remember this, I think the 2 variable and really the 3 variable, all the higher dimensional versions of this are pretty simple. But if you sort of have forgotten about it, it becomes a little complicated. So 2 variable integrals over rectangles. So what is a rectangle? Well, you know what a rectangle is, but let's give ourselves some notation. I'm going to write a rectangle this way. It's going to be a product of intervals. And so if I draw the xy plane here, then what I'll do is I'll take an interval a to b in the x coordinate, an interval c to d in the y coordinate, and I'm just going to look at, essentially you can draw these lines, the vertical and horizontal lines, and get everything inside. That's the interval R. So what we want to do in future classes, and probably even Thursday, is we would like to form integrals over sort of more general domains, not just over rectangles. Because once we go to higher dimensions, it's not like one dimension where the only sort of interesting thing would be a closed interval. Now we have all kinds of shapes that we can draw, and we might want to integrate over those different shapes. But the first step will be just to focus on rectangles. Okay, so now we're going to have f of xy. It's a function with R in its domain. So this domain doesn't have to be R, but it has a container. So what we now want is we want a notion of a definite integral over R, definite integral of f over R. So we want a notion of this. And what we're going to look for here, I mean, we know what the meaning of this is. I mean, we know what we want from the meaning of this, which is if we take the graph of our function, f, and we look at it over R, we want this to be the volume under the graph between the xy plane and the graph of f over R. So that now, of course, just like in one variable calc, we don't want volume really as much as sign volume. So if it crosses the plane, we'll pick up a negative sign or something. So there's some issue there, but putting that aside, assuming, say, f is positive, that's what we're looking for, this definite integral, or this double integral to represent. So how do we do it? Well, we do the same thing we did in one variable, but now we need a lot more notation. So we need a partition. Well, we need choices. So let's see what our choices. The first choice we'll make is a partition. But now the partition, you should think of the partition as being like taking out like a cheese grater, right? Take a cheese grater and take your rectangle and then grate it and then turn the grater around and grate it again, right? Or maybe, I don't know, like some kind of slicer, I don't know. No, I like cheese. So what we're going to do is we're going to partition both the interval AB, and we're going to partition the interval CD. So we're going to choose points x naught through xm and y naught through yn that are increasing and that take our rectangle. Take our rectangle. Let me draw the rectangle. Yeah. So this is our rectangle. What we're going to do, so this is our point AC. This is our point AD. This is BC, BD. And what the points X are going to do, X naught through XN are going to do, is they're going to divide this up this way. And then the points on the, Y naught through YN are going to divide this up this way. Okay. So we get some big mesh here of a bunch of sub-rectangles. And we'll give ourselves some notation. So we'll write Rij for the rectangle given by xi minus 1 xi cross yj minus 1 yj. So we get R11 here, R21, so on, R22, so on and so forth. Now, what do we want? Well, one thing we needed when we calculated the area of these little rectangles in our Riemann sum for one variable is we needed the length of the base. And what we're going to do now is we're going to make sort of rectangular boxes. And so we're going to need now the area of the base. So we want a notion of the area of each of these. So we want del Aij, and this is equal to the area of Rij, which is equal to, if you want, del Xi, Yj, or if you want, you can write it out as just these lengths times each other. So this is just the area of each of these sub-rectangles, but we want this notation. And now, well, we've made our, this is the, so as I said, the notation gets a little more cumbersome. We have to make more choices, but it's the same idea. We're taking our rectangle, we're breaking it up into a bunch of little rectangles. And now we need another collection of choices. Just like in the case of one variable where we needed to choose, as this gentleman said, the height of our rectangles. Now we're going to need the height of our rectangular boxes. And for that, we need to choose sample points inside of each of the rectangles. So we also need to choose sample points, which then consist of two coordinates, xi star, yj star, each of these in their respective rectangle. And then what do we have? So, well, let me make a drawing here. So let's say we have, so let's say this is our rectangle in the XY plane. Here's X, here's Y. And we have some function, some curved function. This is the graph of f, fxy equaling z. And now we've done what we said we were going to do. We broke this up into a bunch of subrectangles. And we chose a sample point. Then what we're going to do is we're going to take this rectangle that we've chosen our sample point in, and we're going to use that sample point to find the height of our function. Once we do, we can make a little rectangular box. Sorry. Well, okay, people hopefully get the idea. You can make a little rectangular box of this height. So this is this box, and the volume of this is going to equal the area of the base, oops, which is denoted as times the height. And the height we'll put first, actually, which is going to be f of xi star yj star of that particular box. But if we're going to get the area under this surface, well, we need to add all of these areas, or an approximation to it. We need to add up each of these boxes. So using our sample points and our partition, we can form this Riemann sum, double Riemann sum. And for that, we have a fancier expression. So you're going to go from I equaling 1 to m. You also need to sum from j equaling 1 to n. You put in, these are the heights, and these are the areas of the base. This is our double Riemann sum. It's an approximation, and if you ask a computer for some funky function to evaluate the area under that function, or the volume, excuse me, under that, under the graph of that function, it will generally compute this for a very fine partition up to some specified error. But we want the exact answer, and if we want the exact answer, we need to make the definition. And the definition is as follows. Definition. So the double integral of f for r is precisely this limit. Well, it's denoted this. So r is this, what I had written before, r is the rectangle we're dealing with. And it's the limit as, again, I'm just going to write it as the partition, sort of it's known as the norm of the partition, but it's sort of you can think of that as the largest area of any rectangle, the largest delta a sub I, tends to 0 of this double Riemann sum. This is the definition. Like it or not, that's what we've got. I should mention, there are more ways of defining integrals. The Riemann integral is one. There's something called the Lebesgue integral, which is a little more mathematically rigorous. And well, this is okay for most functions. Okay. Of course, you always need to add this comment. I'm going to say if the limit exists. So in this case, we say f is integrable. On R. Now, there are theorems that one might want, and we will want, but I'm just going to state them as facts. One is that if f is continuous, it's integrable on a rectangle. So, the vast majority of normal functions you'd write down are in fact integrable. So you don't have anything to worry about. And then all of the properties, so maybe this is one fact, but also all of the properties you would like for integral are there, well, all the basic properties, I should say, are there for double integrals and triple integrals. So in particular, if you take the double integral of a sum, it's the sum of the double integrals. Here I'm omitting the x and y, but okay, you can fill it in. And, you know, similarly, if you take a constant times a function, here I'll put an x, y. So c is a constant. You can pull the constant out. You don't have to make any changes there. So all of these things are not hard to show from just the fact that this works for limits. These things work for limits. Here c is a constant, or scalar if you want. Of course, you can't have it a function of, you can't pull out functions. So, and then, you know, there's also this notion that, you know, if you can, and this becomes a lot more helpful in higher dimensions than maybe it would in one dimension. If you have your rectangle is a sum of two other rectangles, or really other two regions, although we haven't quite defined that yet. So let's say we have not a sum, a union. So let's say our rectangle R is here, and we have two subrectangles. Well, then the integral, the double integral over R of a function is going to be equal to the sum of the double integrals over these subregions, for S and over T. So things that maybe this is a bit new. I mean, of course, you can do this, you know, with intervals as well, but well, when you start breaking up your space in higher dimensions, there's a lot more ways of doing it. Okay, so these are some general facts, and this is the definition of the double integral. Lightning review. But of course, I understand that many of you are not interested, or maybe like feel like, well, that's great, but how do I compute? I understand that there's a need to compute, and there are some amazing theorems now that allow us to do that. And so, but it's important from my perspective for you to know what you're computing. And so this is actually what's being computed, this sort of volume or sine volume under the graph of your function. Okay, so how do we compute? How do we work with these things? For that, we need a notion called an iterated integral. So here's the way an iterated integral looks. It looks just like one of these double integrals, except you're going to put endpoints on your integral. So I'll write down both of them. So we're going to stick with the same rectangle, AB cross CD. And this is an expression for an iterated integral. And let me explain what it is. So the iterated integral is sort of like a partial derivative in a sense, in a very loose sense, which is it says, do the one variable thing, keeping the other variable constant. And then do it sort of one at a time. We'll do an example in a moment. So also, this is you also have a choice in which order you want to do this thing. In other words, you can write it for a double integral, you can write it in one of two ways. And indeed, they're very different as far as practically what you're computing, although, as we'll see in a moment, you might get the same result. Okay. So this is sort of an order of integration. Which order do you want to integrate in? X first and then Y, or Y first then X? It depends. But these by themselves, I want to say, are just formal things. They're just formal gadgets, or calculation techniques. Now, of course, definite integral has meaning. So this does have meaning. But the meaning of this is just the one variable notion of the definite. Okay, so let me explain how to do this through a problem, through computation. So let's compute following iterated integral. So I've got this guy here. Okay, so here's our solution. So this guy is going to be the same. I'm going to use this formula, which is my first formula here, as, well, I'll ignore this first integral from -1 to 1, and I'm going to exclusively focus on the integral in the parentheses for a moment. And there, I really want to pay attention to this dy. In other words, you need to know what you're integrating with respect to. And so here, since my dx is out here, I'm not going to think about it for now. I'm just going to integrate with respect to dy, with respect to y. Which means that in here, I'm treating x like it's a constant. I don't, just like when you take partial derivatives, if you're not taking a partial derivative with respect to a given variable, you just treat it like a constant. So here my x is fixed, and I'm just going to integrate with y, with respect to y, as though x were a constant. So I'll leave everything outside the parentheses alone, and I'll just integrate with respect to y. So here I will get x squared y minus x y squared over 2. And I'm going to evaluate that from y equaling 0 to 1. Then whatever I get, I'll integrate the result afterwards with respect to x. It is, I highly recommend, certainly when you're starting out with these, to really write the variable here, not just go from 0 to 1, because it's easy to forget which variable you're evaluating. Okay, so let's continue to just work within the parentheses. So at 1, I get, at y equaling 1, I get x squared minus x over 2. And then at y equaling 0, I get 0. So then this results in integral from -1 to, the integral from -1 to 1 of x squared minus x over 2 dx. And now we're very much in one variable land. And you'll notice there's no more y. If you have successfully done the first step on your iterated integral, you will have eliminated one of the variables. If you have unsuccessfully done it, there will be one thing that could happen is there will be still 2 variables. So it's something to look for. So here we're going to integrate with respect to x now, and we'll get an x cubed over 3 minus x squared over 4. And here we're going to, okay, so here I don't know if I need to write it, but I will. -1 from 1 to -1, which of course, just to finish it up, will give us 1/3 minus 1/4 minus -1/3 minus 1/4. So get 2/3. Questions? Does it make sense? I'm sorry that you have to integrate again. I know that you want to leave integrals behind, but it is a part of it. Yes. Absolutely. So the question was which I think you said case, but sort of I made a choice here. I think the question was, what did you make a choice more or less? And the answer is yes. I made a choice. In a sense, I made the choice when I wrote it this way. So you can write it the other way. In other words, I could have written it dx then dy. If I did that and I wanted to sort of get the same type of result, I would also need to switch these. And we'll see that in a moment. In fact, we'll see that right now. So there is an amazing theorem called Fubinis Theorem. Other questions? Okay, Fubini's theorem should be thought of as sort of, well, it's as important to multivariable calculus as sort of the fundamental theorem of calculus is to one variable calculus. I mean, there's versions of the fundamental theorem for and we'll get into those for multivariable calculus, but Fubini's theorem allows us to actually compute double integrals, triple integrals, and so on. Without it, it would be sort of impossible to really get any numerical results. So what does it say? It relates these two different notions. It says if f of xy is integrable on this rectangle, I'll rewrite it, then this insane thing we wrote, which was the double integral is massive limit over all possible double Riemann sums, can be computed by actually just doing an iterated integral. Which, as we just saw, was not an insanely difficult thing, at least for reasonable functions. Furthermore, it says that it's not determined what order we do this in. In other words, this choice can be made either way. We can integrate with respect to x first and then y, or the other way around. And we'll still get the same result. So this is sort of, as I said, for fundamental theorem of calculus is a very pragmatic theorem. It says we have this very confusing, difficult definition of something we're really interested in, area under a curve, and we can compute it with some very algorithmic antiderivative thing, some very simple computation. Fubini's theorem is in the same spirit. It's really the same spirit. Okay. Now, I want to illustrate an aspect of Fubini's theorem, which is really this choice that we were talking about. So let's do another problem. It says, let's compute a double integral now using Fubini. And this, I think, actually is in your, just looking over the book, I think this actually is in the book too. I'm not sure I chose the same rectangle, but. All right. So we're going to compute this double integral. So we want to use Fubini and make this double integral into an iterated integral. So I'll rewrite it. Double integral of r x ex y dA. A here stands for area. And I'll just say, okay, that's 0 to 2, 0 to 1, x, xy, dx, dy. Okay, I just sort of chose the first of my, I looked at my theorem and I saw this and I just wrote it down. Okay, well, you guys can help me. So I'm going to do this thing in the parentheses first. Well, how does it look? What is the integral here? I'm going to integrate with respect to x. What do I need to do? Can anyone tell me some general technique? Use substitution. Okay. Other techniques? Yeah. Integration by parts. Anyone want to do trigonometric substitution? Good. You shouldn't want to do that. Good. Yeah, so both of these answers have a place in this question, but I would say right now, the integration by parts answer has a more prominent place. And the point is we really do have to be aware of what we're integrating with respect to. We're integrating with respect to x. So here I need actually an integration by parts. And what I will get is an x over y, e to the xy. And I need to subtract 1 over y squared, I believe, yeah. E to the xy. And I need to evaluate that from x equaling 0 to. How are you guys feeling? I'll take the complete silence as great. Right? Everyone's feeling good. So I compute in the integral from 0 to 2. Now I just have to evaluate at x equaling 1. I'll get e to the y over y minus e to the y over y squared. And then I have to put it at x equaling 0. So the first term vanishes, and then I get a negative. So I get a minus and negative, and I'll get plus 1 over y squared dy. Now I have successfully eliminated one of my variables, right? And I look at my result. How do you guys feel about this? Do you feel good? Okay, well, right. So someone's like burying their head in their hands. And yeah, I would kind of agree. I don't like this integral. I don't know if you guys like this integral. This integral doesn't look good. It doesn't look like fun. This looks like a pathway to integration by parts forever. So all of a sudden, I start feeling uncomfortable. So discomfort. And when I feel uncomfortable in life, right, and I have other things I could have done, I often say, well, maybe I should do that other thing because I'm not comfortable with this thing. Well, luckily, Fubini gives us options. I chose this one, but I didn't have to. Let me go back. Let me try again. Let's do the same thing, same integral, double integral, but now let's do it by integrating with respect to y first. Okay. So I'm going to put everything in parentheses so I can sort of isolate what I'm doing and forget about the other thing for a moment. Okay, now I look at this guy, and there was an answer before when I asked, what should I do here? And someone said substitution, use substitution. And now if I'm fixing x, yeah, that looks very practical. If I'm integrating with respect to y, use substitution looks perfect. Here I'm just going to have e to the xy. And here I'm going from y equaling 0 to 2. All right, if I take the derivative of this with respect to y, this is what I get. So this is the antiderivative with respect to y. This. Here I get something very simple. 0 e to the 2x minus 1 dx. And there. Now I can integrate, oops, keep going. Now I can integrate with respect to x. Life is good. Sorry. 1/2 e to the 2x minus x. Here I'm going from x equaling 0 to 1, which is going to give me 1/2 e squared minus 1 minus 1/2, or 1/2 e squared minus 3x. And I've got my solution. So the lesson here is that Fubini does give you options, and the order of integration, you will get the same answer if you did it correctly either way, but sometimes it's extremely difficult to integrate one way, and it's very easy to do it the other way. So it's not completely symmetric. There are some things that are better. All right, I think we'll end a little early on that today and pick up on Thursday.